start this lecture by quickly recalling what we had done so far. So, recall that I had started with wave on a string. So, I will make the string now, and we had obtained the equation of the wave as d2 f over dt square equals 1 over v square d2 f by dx square. We had taken a one dimensional string, and the solution with a given frequency, which I call the harmonic solutions, were given as f x t as some amplitude sine of omega t minus k x, where k is 2 pi over lambda, and I am going to give it a name now. It is called the wave vector. This was for a continuous string, and then we generalize this to the case where I have these point particles of mass m connected by some spring or interacting with each other, and we made an approximation that only nearest neighbor atoms interact, and under that assumption I also gave the equation for these atoms. Now they are discrete. I had motivated you how to come to a discrete equation, and then we wrote the equation for the displacement of these atoms as d2f over dt square is equal to the coefficient of the interaction times f s plus 1 plus f s minus 1 minus 2 f s, and I am missing a few terms here. There should be a mass term with the displacement, and this is displacement for the sth atom, and then the rest follows. So, what we are doing is we are writing the equation for this sth atom out here. I am showing you on top of the screen. This is interacting with the next atom, s plus 1th atom and s minus 1th atom, only the next nearest atoms, and then this becomes the equation. So, let me write it again in the same color. The equation of motion for this atom at the sth site is d2f s over dt square is equal to c, where c is the spring constant, so to speak, is f s plus 1 plus f s minus 1 minus 2 f s. This is the equation of motion. All atoms are identical, they are interacting with only with nearest neighbors, and then this becomes the equation. And I had also arrived at this equation through finite difference formula for the second derivative. I would urge you to go back and look at the first lecture. So, through all this, what we have said is this is the equation of motion when these atoms are at discrete sites at distances a from each other and are connected through springs, or equivalently they are interacting with forces only with the nearest neighbor, and the force is proportional to the displacement, spring like force. And then we said, since this is a wave equation, this is like the generalization of the wave equation for discrete masses, a solution for a given frequency would also look like f. The difference from the wave equation is, instead of x, now I am going to have s a, where a is the distance between the atoms, at time t is like a sine omega t minus k s a This is the solution that I had proposed last time, and we are going to explore this further this time. So, the only difference between a continuous string and these discrete masses is that now that x that was there in the continuous string has been replaced now by this k S A, and these are sitting at discrete points. Let us now look at the nature of the solution. So, let me write the whole thing all over again. The equation of motion is d2f over dt square is equal to, so there is a mass term, c times f s plus 1, and this is for the sth atom, plus f s minus 1 minus 2 f s, and the solution I am looking for is of the form f at S A, or S, just S is fine, t is equal to some amplitude A sine of omega t minus k S A. Let us take the derivatives. If I take the time derivative, d2f over dt square would be equal to minus omega square A sine of omega t minus k S A. Let us also calculate the right hand side now. So, this is my left hand side. The right hand side is going to be f s plus 1. So, that is going to be A sine of omega t minus k S A minus k A plus f s minus 1. So, that is going to be A sine of omega t minus k S A plus k A minus 2 times f s, which is going to be A sine of omega t minus k S A. Let us calculate this. So, this I am going to write as equal to, first term is going to be A sine of omega t minus k S A times cosine of k A minus A cosine of omega t minus k S A times sine of k A. The second term is going to be plus A sine of omega t minus k S A times cosine of k A plus A times cosine of omega t minus k S A times sine of k A, and there is this third term which I am going to include in the next screen, but for the first two terms you can immediately see that this term cancels with the second term, and I am left with 2A sine omega t minus k S A cosine k A. So, let us see how does it work out. I will go to the next page. So, I am looking for the solution. Let me rewrite this. Looking for the solution of this equation, d2f by dt square times m is equal to c f s plus 1 plus f s minus 1 minus 2 f s, and I have taken the solution to be of the form f s t equals a sine of omega t minus k S A, and then we have found by substituting at n that the left hand side is equal to mass times minus omega square A sine of omega t minus k S A, this is times, and the right hand side is which we calculated just now, is 2a sine of omega t minus ksa times cosine of ka, and the last term was, which I had not included in the previous slide, is 2 times sine of omega t minus ks a. This simplifies to 2a sine of omega t minus ksa times cosine ka minus 1. Equating the two sides of the equation, we now get minus m omega square a sine of omega t minus k s a is equal to 2a sine of omega t minus k s a times cosine of k a minus 1, and this would give me a relationship between omega and k. So, let us now quickly cancel the terms on two sides. I can cancel a on the two sides, I can cancel sine omega t minus k s a on the two sides, and I am left with omega square is equal to 2 over m. I am sorry, there was a c also out here, c 1 minus cosine of k a. Notice that the sign, because of this minus sign out here, the right hand side now has become 1 minus cosine k a. So, let us write this. What we got for the solution of this equation equals c f s plus 1 minus f plus f s minus 1 minus 2 f s, assuming a solution f s equals a sine of omega t minus k s a, we got the relationship omega square is equal to 2 c over m 1 minus cosine of k a, which I can expand and write as 2 c over m 1 minus 1 plus 2 sine square k a by 2. This 1 cancels, and I end up getting that omega square is equal to 4 c over m sine square k a by 2, and therefore, omega as a function of k is given as 2 square root of c over m modulus of sine k a by 2. Modulus because omega is always positive. This is my answer. So, what have we learnt? Let us understand that. What we have learnt is that given a one dimensional chain, it is an infinitely long chain of atoms which are at a distance a from each other and interact with each other through a force proportional to the distance or the elongation of the spring C x, then if I disturb one of the atoms, right, I will just disturb it. If I give it a push, if I do it properly, I can have harmonic waves here traveling with frequency omega square related to the k as sine k a by 2 modulus, because it is positive. Let me again put it in a box. Recall, what is k? K is 2 pi over lambda. So, the picture that is coming to our mind now is that if I have this chain, am not bothering to make spring again and again, right. And if I give it a displacement, let me give something a displacement, and the displacement is such that it has a wavelength lambda, that means the displacement would go something like, let us say, right, this distance being lambda. Then these atoms, let me now show it in a different color. The atoms would be displaced at each point, right, by, and show it in green. This atom remains where it is. This atom would be displaced here. This atom would be displaced here. This atom would be displaced down here. This atom would be displaced here, and so on. In the whole chain, these atoms will be displaced like this, and they would be oscillating just like in a wave. They would be oscillating back and forth. With the amplitude omega, so let me write this, no sorry, with the amplitude A and frequency omega, right, frequency omega given by this formula out here. So, we have found a relationship like we have for waves in a medium like the sound waves, or you may have studied electromagnetic waves. There is a relationship between the frequency and the lambda. Similar relationship exists between omega and k for harmonic waves, and this is the picture that we make, and they will be oscillating back and forth, and this wave travels. The difference is that now the systems or the atoms that are oscillating back and forth and that are propagating the waves are at discrete points. It is not a continuous medium. So, let me recap now the whole thing again. In this discrete system, I have a wave where the atoms now get displaced like this at a given time, and as the wave propagates, next time the wave would have shifted further out, and these displacement of the atoms would be different, right, according to where the position of the wave is. So, this wave is propagating and these atoms are going back and forth with a frequency given by 2 square root of c by m modulus sine k a by 2. Okay. Now, let us look at how this plot looks. If I were to plot omega versus k, at k equals 0, everything is 0. As you increase k, it will go up like a sine wave and then it flattens out. Same thing on the other side, it flattens out and it hits a maximum at pi over a, hits a maximum at minus pi over a. Remember, there is a mod in the formula, so minus pi over a and pi over a does not matter. And if you increase k further, it goes down, again becoming 0 at 2 pi over a, minus 2 pi over a, and if I increase k further, it repeats itself. This is the picture of omega k versus k. So, what you see is that omega has a periodic behavior. It is linear near the origin, like the sine curves for a small magnitude are linear near the origin, then flattens out and then repeats itself. So, omega actually can be determined by all k's only up to pi over a, from minus pi over a to pi over a. After that it repeats itself. So, I am just going to make a statement and then justify it further, that only k in the range pi over a and minus pi over a are the only relevant k's to describe the behavior of vibration of this discrete lattice. Let me justify it further. See, omega does not change, but does it mean anything more? So, if we say, let me write the formula again, omega k is equal to 2 square root of c over m sine of k a by 2 modulus. If we say this, notice that k we are saying is minus pi by a to pi by a are the only relevant k's to describe the vibrations of a lattice. What happens if I go beyond pi over a, right? So, suppose I take, let me make this picture again. This was my picture for omega versus k up to pi over a and minus pi over a, and suppose I take a particular k point here and move it by 2 pi over a. That means, I take a new k prime which is equal to 2 pi over a plus k. What happens to omega? Omega will become 2 root c over m mod sine of pi plus k mod, which is same as sine k. So, omega does not change. What about the displacements? Let us look at the displacements. What would happen is that when I take these points and I take a particular k or a lambda. So, let me make a lambda. These points are displaced at a given time like this, which I am showing in purple. What will happen if I take a k prime which is 2 pi over k? So, let us analyze it little. So, when I take a k, the relevant lambda is 2 pi over k. When I say mod k is less than equal to pi over a, this implies that lambda is greater than or equal to 2 pi over pi over a, that is equal to 2a. So, what we are saying essentially by saying that k confined between minus pi over a and a is the only relevant quantity also implies that lambda greater than or equal to 2a is enough to describe wave in a lattice. What happens if I take shorter lambda? So, suppose I take a shorter lambda. What you would find if I take a shorter lambda which corresponds to, right. So, let me take a shorter lambda, lambda prime, which corresponds to some k prime which is 2 pi over a plus k, right. You can calculate this, and what you would find is that the motion, if I plot this curve, right. Suppose I take a shorter lambda, you would find that each point is given the same displacement by the shorter lambda, and also its motion direction is the same. So, it does not matter whether I take lambda to be shorter corresponding to k prime or that lambda larger than 2a. Let me now show this mathematically. Recall that we have f s t written as an amplitude e raised to I k s a minus omega t, or equivalently as cosine of k s a minus omega t, or a sine k s a minus omega t. They are all the same thing. The only thing is that here we take the real part and a could be complex. This I explain further in my note that I will give to you. Now, if I take k prime is equal to k plus some integer n 2 pi by a, then k prime s a is going to be equal to k s a plus n times 2 pi by a times s a. So, this becomes k s a plus 2 pi times n s, where n is an integer. So, I can add 2 pi by a or any integer multiple of it, and at the same time I have omega k prime is equal to omega k, that we have already discussed quite in detail, and therefore, the displacement f s t, which was given as some amplitude e raised to I k s a minus omega t, for k prime it is going to be f s t is equal to a e raised to I k prime s a minus omega k prime t, which is equal to a e raised to I from whatever we did in the previous slide, k s a minus omega t times e raised to I 2 pi n s. Now, n and s both are integers, therefore, e raised to I 2 pi n s is equal to 1, and we find that f s t is the same for k, and k prime is equal to k plus 2 pi over a times an integer n. So, again we see that if I take k confined to range between pi by a and minus pi by a, it describes all the motion of this discrete lattice, because adding 2 pi by a to it does not really make any difference in the frequency or the displacement. One more point you may ask is, fine, the displacement is the same, what about the velocity? So, when I have this wave, and I am claiming that with a lambda like this, where the particles are displaced like this, and another lambda which is shorter like this, gives the same vibrations, then we have found that f s t is the same for k, and k prime equals k plus 2 pi by a times n, and the velocity v is nothing but d f by d t. Let me put a subscript s here just to show for the sth position, and this is d by dt of a e raised to I k s a minus omega t, which is nothing but minus I omega f s t. So, if the displacement Fs remains the same, so does the velocity. So, all these atoms have the same displacement, same velocity, and you can also show same acceleration. So, it does not really matter whether I take k confined in the Brillouin zone or k outside it, the motion is the same, and therefore, everything can be described with k's within the Brillouin zone. What I will do is, I will make a nice picture and give a supplement to this to convince you that it is k between pi by a and minus pi by a, that really is enough to describe the motion, because omega anyway is the same, and lambda therefore, I take 2a or greater, any shorter lambda also gives you the same motion. So, with this I will conclude this lecture is by saying that 1, in a discrete lattice with, I keep making this spring again because I want to show that this force is proportional to c times displacement, mass is m, then the equation of motion is d2f by dt square is equal to c f s plus 1 plus f s minus 1 minus 2 f s, and the solution f s t is wave like with an amplitude a and frequency sin omega t minus k s a, and the relationship between omega and k is 2 root c over m sin mod k a over 2, and k between pi by a and minus pi by a, or equivalently lambda greater than or equal to 2a is sufficient to describe the motion in this discrete lattice. So, now some terminology. This extent of k from minus pi by a to pi by a is known as Brillouin zone, and you will find in all the crystal properties is the Brillouin zone, whatever happens inside this keeps repeating itself. So, this is a very important concept. It is known as Brillouin zone, all right, and all k dependent quantities can be described completely by k's inside the Brillouin zone. So, this is the conclusion. So, this is the point number 2, and I have taken a particular kind of solution. In describing solution, I took f s t to be a sin omega t minus k s times a. You could have taken equally well f s t as a cosine of omega t minus k s a. Equally well, you could have taken f s t as a sine of k s a minus omega t, or f s t is equal to a cosine k s a minus omega t, does not matter, you change the sign and phase changes, and generally make maths easy. What you do is you combine all this and write your f s t as some amplitude e raised to I k s a minus omega t, because when you do this, adding, subtracting, multiplying, taking differentiation, that becomes easy. And finally, it is understood when you do this, finally when you are going to show the displacement is going to be real of this a e raised to I k s a minus omega t, or imaginary part of this. So, in the books, this is what is followed. If you read the reference books that we have prescribed, you will see that the solution is given as e raised to I k s a minus omega t, and sometimes it is confusing because a lot of students ask, if this is a complex quantity, how is the displacement given? Displacement is given as its real part, and that is precisely when I did the exercise, I showed you that I can do the same calculations with displacement taken as real. But to facilitate the mathematics, one does it with exponential, and this is what you will find in most of the books.